The most distant human-made object is NASA's Voyager 1 spacecraft, which has ventured into interstellar space. Launched over 45 years ago, it continues to explore regions far beyond its original mission parameters, surpassing its expected lifespan. This remarkable journey redefines our understanding of space exploration. What's even more astounding is that this resilient spacecraft, now billions of miles from Earth, still transmits data using technology older than a cassette player. Recently, Voyager 1 made a discovery that has captivated the scientific community and the world at large. What could this extraordinary find in the depths of space signify for us here on Earth? A pivotal moment in space exploration history occurred when two groundbreaking missions were launched, marking the dawn of a new era. Thanks to the ingenuity of Gary Flandreau at NASA's Jet Propulsion Laboratory, an optimal trajectory was charted for a probe to reach the distant planets Jupiter, Saturn, Uranus, and Neptune. Using just a pencil and a 20th century engineering tool, Flandreau discovered that in the late 1970s and early 1980s, the four gas giants would align in a unique cosmic configuration, forming a celestial necklace with Earth. This alignment would allow a spacecraft to gain speed by utilizing each planet's gravity, effectively being pulled along by an invisible rope. This gravitational assistance meant that a journey from Earth to Neptune, which would typically take 30 years, could be completed in just 12. However, this rare planetary alignment occurs only once every 176 years. Seizing this fleeting opportunity, NASA swiftly launched two identical spacecraft, Voyager 1 and Voyager 2, in the summer of 1977, just 15 days apart, to capitalize on this cosmic event. Unbeknownst to them, these twin explorers would go on to shatter all records in space mission history. Over 45 years since their launch, Voyager 1 and Voyager 2 remain operational, continuously sending back data from the fringes of our solar system. These probes have ventured farther than any spacecraft before, far exceeding initial expectations, especially considering their original mission was slated to last only 4 years. Early in their journeys, these interstellar pioneers surprised scientists with close-up images of Jupiter and Saturn's moons, revealing unexpectedly active and dynamic worlds. Discoveries of active volcanoes and ice fields revolutionized our understanding of these distant celestial bodies. Voyager 2, in particular, became the first spacecraft to approach Uranus in 1986 and Neptune in 1989, making it the only probe to have visited these planets and unveiling astonishing findings in previously unexplored territories. More than 14 billion kilometers from Earth, these Volkswagen Beetle-sized probes have defied all expectations, continually expanding the horizons of our knowledge. Voyager's journey commenced with a gravity-assisted maneuver around Venus, a feat never before attempted by any spacecraft en route to Mercury, solidifying their status as true pioneers. The voyage to Jupiter required traversing a distance 10 times that from Earth to Mercury and navigating the perilous asteroid belt, a challenge previously undertaken by the Pioneer 10 and 11 probes. Equipped with just 69 kilobytes of memory, a mere fraction of a modern smartphone's capacity, the onboard computers had to autonomously manage the complexities of this extraordinary mission. Data collected by Voyager's instruments was stored on 8-track tape recorders before being transmitted to Earth via a 23-watt transmitter, consuming about the same power as a light bulb. The spacecraft featured 12-foot diameter satellite dishes to facilitate communication, utilizing light-speed radio waves to send and receive messages. However, the increasing distance from Earth, advancing by 3 or 4 light seconds each day, posed significant challenges. Despite these obstacles, the Voyager probes have consistently surpassed expectations, astonishing astronomers with unexpected discoveries in the interstellar void. Their journey has redefined our comprehension of the cosmos and transformed our perspective of the unknown. Beyond our solar system lies the enigmatic Oort cloud, a vast assembly of comet-like objects bound by the Sun's gravity, extending toward the nearest star. While the Voyagers are gradually approaching this distant realm, their entry into interstellar space was marked by crossing the heliopause, the boundary between our solar system and interstellar space. Initially estimated to be about 50 astronomical units from Earth, this boundary's crossing prompted continued funding for the mission as the probes neared this milestone. However, the transition did not immediately reveal environmental changes, leaving scientists perplexed. The passage into interstellar space was anticipated to coincide with a sudden increase in cosmic rays, high-energy particles traveling near light speed, emitted by supernova and other cosmic phenomena. Yet, most high-energy rays are deflected by the heliosphere's magnetic shield, which safeguards our solar system from external threats. The Voyager mission team also closely monitored shifts in the prevailing magnetic field as the spacecraft ventured into the interstellar medium, an environment composed of ionized gases influenced by nearby stars. This interstellar magnetic field was expected to differ in orientation from the heliospheres. However, the Voyager probes did not detect significant changes in the magnetic field. On August 25, 2012, Voyager 1 finally crossed the heliopause, transmitting compelling data that confirmed the anticipated increase in plasma density, albeit without evidence of magnetic field changes. This unexpected finding sparked intense debate within the scientific community. If the magnetic field remained largely unchanged upon crossing the heliopause, what implications did this have for our understanding of the interstellar medium and our solar system's interaction with its environment? By entering this new region, known as interstellar space, Voyager 1 provided a direct glimpse into an unexplored area, yet it also raised more questions than answers. One early theory proposed that the interstellar magnetic field might align unexpectedly with the solar field, creating a smooth transition rather than an abrupt cutoff. This would suggest that the forces shaping our cosmic neighborhood are more intricate than previously imagined. The data also revealed a noticeable increase in high-energy cosmic ray particles from outside the solar system, confirming that Voyager 1 had officially exited the protective bubble of solar influence known as the heliosphere. However, the mystery persisted. If there was no marked change in the magnetic field, how far was the probe from a region entirely dominated by the interstellar medium? Some scientists speculated that there might be a more extensive transition zone than anticipated, a region where the sun's effects subtly interact with the interstellar environment. Others suggested that the heliopause might not be a clearly defined boundary, but rather a fluctuating border influenced by factors such as the solar cycle or the pressure exerted by the interstellar medium. As Voyager 1 continued its journey beyond the heliopause, the data it transmitted back to Earth challenged long-held assumptions. Analysis of plasma density revealed unexpected fluctuations, indicating that interstellar space was far from the uniform vacuum once envisioned. Instead of an endless expanse of homogeneity, this vast frontier appeared to consist of plasma pockets, each with distinct densities, temperatures, and energy levels. These findings puzzled scientists. Theoretical models had suggested that the interstellar medium should be relatively uniform, shaped over eons by the consistent pressure of stellar winds and cosmic radiation. Yet, Voyager 1's instruments painted a different picture. Within a single week of observations, the probe detected shifts in plasma density, suggesting it was navigating through regions with vastly different characteristics, some denser and hotter, others surprisingly sparse and cold. The variations were so pronounced that researchers began referring to these pockets as plasma clouds. Further study revealed that these clouds seem to align with traces of ancient supernova remnants, implying that the interstellar medium might bear the imprint of catastrophic stellar events from millions of years ago. Each pocket could be a relic, carrying clues about the violent history of our galaxy. Let us know your thoughts in the comments below. If you enjoyed this video, don't forget to like and subscribe to our channel. See you very soon.